Okay, today we're gonna solve all the hardware challenges in the HTB CTF. So the first challenge is pretty easy. You just download the files, and inside one of these folders is a PDF, and here you can find the flag. So this is a warm-up challenge. And so for the second challenge, we have access to a RabbitMQ instance. And as mentioned here, we can use the default credentials, and the default credential for this RabbitMQ instance is admin and guest. So we can test it here. Okay. And it appears that we have to dig into this service to see what we can find. So if you search a little, you can find queues, and inside these queues we have some messages that are ready to be consumed. So what we can do is that we can write a simple code that first tries to connect to this web app, and then it tries to extract all the queue names, and then we can ask the server to see what is inside the queue, and then we can search for the flag. So if we run this, we get the flag. It's so these two questions were the very easy ones, and let's get to the easy question. Okay, so the next challenge is also using an TheProm. We can connect to this via the netcat command, and you can see our old diagram of the TheProm. So the goal is to set up this chip, and then we can use the read byte command to read some data. So if you just search this into the internet and look for the datasheet, you will end up with this PDF file, and the top view here also matches what we have seen in the challenge. So what we have to do is that we need to read the data, and it's mentioned here. So we have to provide CE and OE to low, and we have to set the WE to high. So low and high in the terms of hardware usually means anything less than 3.3 is low. Maybe here it's using 3.8, but we will just set this to 0, and WE should be usually around this voltage or 5. So let's just set this up in the code. So we will first set the CE, OE, and WE pins to 0, 0, which are low, and 5, which is high. So if we just execute this part of the data, okay, now let's read the bytes. So we can see that there is nothing at this address, so it's completely empty. So the thing is that here we will need to set the address, and another thing that is important is that inside this PDF it's mentioned that by providing a 9 pin to 12 voltage, you can read additional data locations, and the length of this extra storage is 32 bytes. So I realized that this might be a place that the flag is stored. So what we have to do now is that we use this address and pass this into the A pins, which were which are here. So from A0 to A7, we have them here, and A8, A9, and A10 are mentioned here. So you don't have to actually modify this part, because we can use the set address pins function, which is mentioned. So what we have to do is that we will first write a loop to go through the starting address of the secret registers to plus 32 more addresses. So we have the address here. We will first convert this into binary, and we drop the 0p part. And then this will be just 0 and 1s. So we will then convert the 1 bits to 5. So it will be 5 voltage, and the 0 can be used for the rest of the pins, so they stay the same. But the A9 pin, which is the second pin in our list, should use a voltage of 12. And then for each of these bytes, we will execute a read byte. So we will just read this address, and then next, and the next, and forth on. So after all, we will decode the response from the server and parse it from hex, and then convert it to a ASCII character, and this should solve the challenge. Okay, the last challenge, which is the hardest challenge, gives us a source code. So we can see that in the source code, we can interact with this device, just similar to the RIDS challenge. But the first difference is that it's using a flag address with a specific address. So at the end, we know that we can read the flag from this address. But if you just read this right now, you will get nothing. And the structure is similar to the first challenge. But we have access to a log underline events.c file that stores the log. So it's pretty long C file. So if you first read the description, it says that there are some logs in the system, and we have to modify the logs directly on the chip to avoid detection, and we have to alter only the user ID with this specific ID. So the register logs related to this ID points to a different ID. So we have to manipulate the memory on this device. And the rest of the logs stored in the memory must remain as is. So we cannot simply remove the storage. We have to keep the integrity of the system. So let's just have a higher look at this file. So here we can see it's using the previously used chip. So and it's using the SPI protocol to communicate. Right now we don't want to play with this part. What more we are interested is how does this exactly work. So we know that we have a CRC and a key size. So there will be CRC data redundancy check and encryption involved. So let's just find an interesting start point. So I think we can start with the log event, which simply logs the event. So it's a pretty long code, but the interesting part is that it first tries to erase a sector. So and the sector ID is 0, and so the sector is part of this TheProm that we can store the data and read from. And here we can see that it's using the size of a smart log event structure plus the size of integer with 32 bits. So Here we know that this will be 4 bytes, but we are not sure about the size of this part, and we will check it later. But for now, we know that after each like event, we will need to use the CRC of this structure as well. So if we want to modify the smart like event, we will have to recalculate the CRC32 as well. So here we have the calculate CRC32 being used, and it's implemented here. So it's just some mathematical and bit manipulation, and we can simply convert this to Python. So let's get back to understanding how this exactly work. So after everything is calculated, it will have timestamp, event type, user ID, and other things. And user ID is the field that we are interested at, and we want to modify it. So after everything is shown for debugging purposes, it will write the data into the flash. So let's go to the write to flash function. The write to flash function will accept the data as a pointer, and it will pass the pointer to the encrypt data function, and then it will page write the data. So page write and sector and things like that are all related to this device. So for now, let's go to the encrypt data function. So encrypt data function, as we mentioned again, will accept the data as a pointer. And the first interesting thing is that it will first read the security register. And here we have the register number and this one, which is, I think, hard-coded. Yeah, so it's mentioned in the comment. So the first argument is the register number. A second one is the address. So I think it's a security register address. So to decrypt the data, we will first need to read the security registers in our exploit. And then we will have to calculate the CRC32 of the data. And this does not include the CRC of the previous data. So it's not something important for now. For now, we have to understand that it only tries to read the data and encrypt it. And then after everything is done to write it, it will only replace the data. So the CRC part is calculated before the encryption is applied, which makes sense because if we are, it's safer to protect the data. Only someone who can modify the actual data before encryption can update the CRC. So one interesting thing about here is that our structure at the first glance may seem to have 4 bytes here, 5, 7, 8, 9. So at the first glance, it looks like that this structure have only 9 bytes, but in reality, this does have 12. So I thought maybe it's an interesting example for you to see this in action. So here we have two structures with the exact same members, but the order of these members are different. So here we have the biggest members first, 2 bytes, 2 bytes, and in total it should have 6 bytes, and this one also should have 6 bytes. So the members are the same. But if we try to execute this code, interestingly, we will see that these structures have different sizes. So the first one have 6 bytes and the second one have 8 bytes. So the reason for that is that some paddings are applied in the compiler to align the members inside the structure. So these structures also will not have 9 bytes. If we just try to see this code, here we have 12 bytes. So we know that our data in the memory will have exactly 12 bytes and also 4 bytes for the CRC. So I think I have the final code here. Yes. Okay. Okay, so we have the flag address here, and for now, it was mentioned in the challenge. We don't have access to this right now. And I have defined some helper functions. The first one is the crcc_do, which was mentioned in the C file. I only changed this to work in Python. Here I have another helper function that accepts the full memory, the user ID you're looking for, and the key. And it will try to go to different offsets in the memory and decrypts the user. So here you can see that it just tries to yield the offset in the memory and the decrypted data only when the sequence is in list. So the sequence is the user ID. So whenever we see the user ID in the decrypted text, we just yield this function, because this is the main part that we are interested to modify. So to interact with this device, you will have to read the datasheet several times. I think it was the most time-consuming part of the challenge. So I just want to go very briefly over the datasheet and the code that we are using. So we have the read command here, which was also previously used, and some other commands, right, like page program, enable write, erase sector, and register secret command read. And according to the datasheet, read security registers. So according to the datasheet here, we can see that if we use 48 in hex, which is this command, and give it some register secret addresses, which are mentioned here, we can read the security registers which store the key. So the first byte, the OSB byte, should be 52, and we extracted this from the log event file here. And the second byte should have this value. It's splitted into 2 cells here. So I just added this in binary, and the third byte should be 0. So here we have the register secret address. Simply we can concatenate them, and we know the key and secret key length was 12, so we can simply extract the key with this command. And then we have the user ID splitted here. And now we will need to read the full sector. I think it was mentioned here, not sure. Yeah, so each sector have this exact size. So I want to read the whole sector with this read command from the first byte. And then what we want to do is that we find a normal user. I found these IDs before just by simply executing this find black. So here I'm simply trying to find a different user ID. I did this manually before, and this is the exact address for that user, and the next 12 byte are the full size of that block. So after I extracted that, I can see that the user ID will be stored in these bytes. I can just check this manually by printing the structure and compare it with the structure mentioned in the like event.c. You can simply compare these fields and compare them with the printed part. So then I store the 2 bytes of this user ID, which is, let's say, the victim ID that we want to modify our logs to be the logs for that ID in these 2 variables. And then I will try to find any place in the memory that have the mentioned user ID. So here I get the offset and the data. So the first thing I do is that I will change that part of data to point to another user ID. Then I will have to calculate the CRC32 of the data, and I will convert this to bytes with Little Indian encoding. And then this is the encryption part. So here you will need to first need to encrypt the data. Or something that I forgot to mention was the encryption mechanism. So the encryption is pretty simple. It's just a simple XOR. Yeah, here you can see it goes through each byte of data, and it will XORs the data with cyclic iteration over the key bytes. So I also implemented this, and encryption and decryption are completely the same thing here because it's using a simple XOR. So here I will try to encrypt this data, not decrypt. In the implementation, they are both the same thing. So I will first encrypt this part of data with the extracted key that we got here before, and update this in the extracted memory from the sector. And then I will have to update the CRC part as well. So now we have the modified memory locally available, but the issue is that we cannot simply send a command to this TheProm to say that we want to write a specific byte in the storage. So we will have to first erase completely the sector and then write back to it. So many times it mentions in the datasheet that you will have to call enable write command for each writing command you want to execute. So I will enable write, and then I will erase the sector. Then I will have to write the new data into the sector. So you can write the data byte by byte. I'm not sure if I can optimize it more or not, but We will have to do this with page program command. We look this in the datasheet. Or maybe just search for the example. It's this one. So the page program allows writing from 1 byte to 256 bytes, and this is called a page. And if you just read this carefully, it says that if an entire page is to be programmed, the last address byte, the LSB addresses, should be set to 0. And if it's not the 0, the number of clocks is 0, so it doesn't matter for us because we want to just write the full page. Okay, so here we will execute the page program command, and the list byte is 0 and the MSB byte is also 0. And for each iteration, I just want to mention that each part of data I want to write, so I will have to just shift this 1 byte to write, and the next data is that the next part is that the data that I want to write to the memory, so I will just pass it a page. So each time in the loop you will have to enable the write command, and finally everything is ready. We can read it back to make sure that this new memory matches the new memory that we provided. And then we can use the flag address by read command and just print everything is there. So let's just test it out with the new address. And this is a final pack. So overall, it was a really fun CTF. So in total, we solved 53 challenges out of 67. Okay, so that's it for the video. See you.